Okay, good.
All right, then welcome everybody to the second invited talk for today. Our speaker will be Daniel Keren. So it's a great honor to have you here. Thanks a lot. Daniel Keren is the chair of computer science
Thank you.
at Haifa University. He has been working in distributed monitoring and machine learning since ages, so pioneering the field in some way with the Lift project and then later in the Ferrari project, at least in the European sector. So usually he's meddling with geometric properties of functions, and he has applied this to distributed learning in a really interesting way. And today he will be talking about regression over distributed data streams, and I'm very excited about this talk. So thanks a lot, Danny, and with that, I'll give over to you.
Okay, thank you very much, Michael. I will start, and just let me check the time. Okay, good. So I will talk about something which is related to machine learning and modeling, but it's really just one example of many problems which can be solved over distributed data streams. And I chose this as a typical example. We actually have a new paper which does something which is similar to this, but quite more complicated for machine learning, for classifying. But I decided not to talk about it because I just will not have the time. And anyway, I prefer to convey the general idea. So let us start. And let us very quickly go over least square regression. Now, all of you know what least square regression is. We have inputs, x, vectors. We have, for each vector xi, we have a scalar, which is associated with it, which is yi. And you're looking for something which will minimize the error of this expression. Okay, so it's just really, very, very basic problem, just finding a linear model to describe your data. And you probably all know the solution. The solution is straightforward. This is something which you only need the second course in calculus and linear algebra to understand. So nothing new here. Okay, this is trivial. But do feel free to stop me with any question you may have. But I'm so far assuming that this is something which is well known. When does this old and simple problem become interesting? When you have multiple nodes, okay? So you have multiple nodes in a distributed system, and I'm assuming that the data is really distributed, which means that you cannot store your data, you cannot centralize it, okay? Because then everything becomes quite simple. Now, every node sees a different data stream, which is possibly very quickly entering and leaving it, and every node keeps a sliding window. But the data, the phenomena which they are monitoring is one. Okay, so what you want to do, and this is the difficulty of the problem, you want to find a global model, okay, and you want to know that it is correct, but not for each node separately, but for the union of the data. Okay, so I hope that the difficulty in this problem is clear, and I will further elaborate on it before I continue with the solution. Okay, now if you were in an environment in which communication doesn't cost you anything, and in which computation doesn't cost you anything, then of course you have a trivial solution. You just choose the coordinator node C. Everybody keeps sending their data to the coordinator in 0 time and 0 money. The coordinator keeps calculating on the fly this vector, this beta vector, and everything is fine. However, that is, of course, completely unrealistic, especially if the nodes are small ones. And as probably all of you know, the main source of power, which is required, is the communication as opposed to calculation. Okay, so we want to compute this beta, this model, with minimal communication. Okay, Let us look at an even simpler problem, computing the variance of data. Okay, and we kind of like this problem. Michael must be grinning because he's probably seen it a dozen times at least. But this is a very simple problem, but which does reflect something on the global problem. So you have node 1, which keeps 4 scalars. Okay, I'm just talking about the variance of a bunch of scalars. Node 1 sees a very nice and tight cluster of data, and the variance is 0.25. Node 2 also sees a very small data cluster, very nice and small cluster. And node number 2 also thinks that the variance is 0.25. However, the variance of the union is, of course, huge. Okay, so this trivial problem hopefully illustrates the difficulty in geometric monitoring. It's not enough that each node by itself sees a nice picture. The problem is with the union. Okay, and further, to make this problem even more annoying, suppose that you know in advance, suppose that this is the initial data here, the upper table, and you look at it, and you see that the variance is 625 or something. So I say, okay, good, I can live with that, but I want to know whether the variance had increased, okay? Now, your data over time, and node number 1 did not change. In node number 2, the data changed from 51, 52, etc., to 91, 92, etc. Now, node 1 and node 2 are both very happy because their variance did not increase over time. However, this is really trivial stuff. The global variance increased a lot. So what this tells you is, and this is the basic observation here, is that for non-trivial functions, for example, functions which are not linear, you cannot infer anything about the global value from the local values. And this is the key point to remember. So if you are lost here, then do feel welcome to interfere and ask questions. Okay. Now, what happens with least squares? It's kind of a similar question, but however, much more complicated because the function which relates the linear classifier, the linear model, to the data is not just a variance, which is a really very simple function, but is quite more complicated. However, conceptually, it's the same, okay? You have a least square model beta, which is computed over the union of the data. And what you want to know is that it did not change by more than a given threshold. Of course, it's totally impossible to keep computing it, okay? So we relax this the requirement that in each and every point in time, you will know the global model. We have to forego this, right? Because then you will have to communicate each time, even if one vector changes in one node, you will have to communicate. So this is unrealistic. So we relax the problem to the problem of, okay, I will not know the current beta exactly, but I will at least be able to submit an alert if there is danger that it changed by more than a given threshold with respect to the data I had in the initial running of this system. Okay, so I will skip all the sum of the, okay? And what we want to say here is that very typically, beta does not change by much, okay? And therefore, you definitely don't want to keep sending data and computing it, okay? So we are not interested in distributed computation. That's a huge problem, and everyone who was in ECML or ICML or all these, in NIPS, there are many talks about distributed computation. We are interested in distributed monitoring, okay? We don't want to keep computing the correct data. We only want to submit an alert if there's a danger that it changed by more than a given threshold. Okay, so far so good? Okay. So how do we do it? Some old papers do something very simple, but quite inefficient. They say, okay, look, I don't know what to do. The function is complicated. I will simply keep periodically checking it. Okay, I will not centralize and compute in every second, but every 5 minutes. There are obvious problems with that. First of all, you may miss. Okay, the model may have changed and you simply missed it because it fell between something changed 1 second after you sample the data for the last time. And also there is no control over the error. Okay, this is a very, very naive algorithm, although it has been used for some practical problems, but I will not spend too much time on it. And let's just continue. Okay. There's also another question which I want to address, is whether the prediction error has changed or the model itself has changed. Obviously, the prediction error in a linear model is quite simple. It's simply a quadratic function. And this is, of course, the famous R2 error. However, the more difficult question, but more interesting one, is to monitor the vector beta itself. I want to emphasize this, and I hope it doesn't appear as if I'm nitpicking. There is the model, and there is the model error, okay? Sometimes it may be, for some reason, you may decide that you're content with just looking at the model error. However, possibly the model itself changed by a great deal, and it's not reflected in the error. So what we tackle here is the question of the model itself, not just the error, but the model beta itself. And we want to see whether it changed. And I will not bother you with the details, but this is some example on real data, but never mind, we don't have time for that. Okay, so what we want to present is this distributed least square regression. And as far as we know, it was the first communication efficient monitoring for least square fitting. Okay, so what do we want to do? Okay, so we have this beta, which keeps changing. We have beta 0, which is the value of the model at time 0 when the system was initialized. The user supplies an epsilon, and we want to submit an alert whenever there's a danger that this inequality is violated. So what we want to do is very simple. We want to guarantee that as long as we do not communicate, then this condition holds, and we communicate only if there's a danger that it was violated. Obviously, you will never find an if and only if condition. You will have false alarms, but we will try to minimize the number. Now, what is a false alarm? False alarm is that one of the nodes says, look, I'm afraid that this condition is violated. And then it contacts the coordinator does something else, maybe it collects the data from all the other nodes, and says, look, you set me a false alarm because I computed beta and it's still very close to beta 0. This is, of course, completely unavoidable, but as I said, we want to minimize the danger of that happening. And these are some of the advantages. Communication reduction was usually by at least 1, typically 2 orders of magnitude. And yeah, of course, if the system is stable, there's basically 0 communication. And some other nicer things. I mean, this is not a probabilistic algorithm. As long as you're silent, then with probability 1, your beta did not change by more than this threshold, epsilon. Okay, now what makes this problem interesting? It's the problem of that you have this ugly thing, which is the inverse of a matrix, okay? This is your equation, this very, very basic equation. Now, what you have to remember is that this vector x, which represents the data, is distributed. Therefore, this matrix is a sum of local matrices. Now, if you have 3 nodes, then you're dealing with the intricate problem that every node knows only its own matrix. And you have to look at the inverse of the sum of the matrices, which is, of course, not a simple problem, okay? So this model, although it's simple to write, is highly nonlinear. And as I said before, this problem was solved in earlier papers, starting, I think, at 2005, 2006, but mostly for linear models, which are much easier, okay? And we are tackling more general problems, which include this matrix inversion. Okay. And this is a difficult problem, okay? Because once again, some simple example, you look at the initial data, this orange is line is one node, this is another node, and you see that the slope, and well, I don't have time to go over the details, but the data near the origin is the time 0, and later it turns to this data. So you see that even in this trivial example, the slope of the blue line does not change. So the node which holds the blue data is very happy because its model does not change over time. Same for this guy, which holds the orange data. However, obviously, the global data, okay, has changed. And the original line, the original least square regression, trivial in this case, it's just a plane, a 2-dimensional data, changed from the green to the purple. So you have this huge change, although, as I said before, every node locally is very happy with its original model and doesn't think that anything bad happened, okay? And it's obvious that this change can be unbounded, okay? There's no way to locally monitor this problem. Okay, so what we want to do is the following. We want to look at this problem of, and now we come to the general framework, which we call, as Michal noted, geometric monitoring. And I will, because time is running out, I will simply jump to the solution. The solution is the following, okay? You express your solution as a general function v, okay, over, which is, and this v hat is the union of data at the local streams, okay? And every problem, every model that you want to define can be defined as a threshold function. So this condition here, what does it tell you? It tells you that the global beta did not divert from the original beta 0, by more than epsilon. And so this is the good set, and we call it the admissible region, okay? And everything which is not in the admissible region is bad. So this is the geometric formulation of the problem. This is why we call it geometric monitoring. Now, this F can be, of course, very complicated, highly nonlinear. For example, as I said, it contains matrix inversions, etc. But V is the average of the local vectors. So now you have a very, now, if you can say something about this admissible region, then your situation seems to be much better, okay? Then the problem becomes a very simple geometric problem. Every node holds local vectors. And the question, now you don't have any function, you don't have anything. The question is the average vector contained in this set, in the admissible region? So this seems like a much easier problem, and it is easier conceptually. However, there's, of course, a problem, okay? As you know, generally, sets in Euclidean space are not closed under averaging, okay? So you may have one vector here and another vector here. I hope that you follow my the mouse. And the average is here. okay? So, and here comes the difficult problem, is to find a convex subset of this admissible region. Now, how is convex related to everything I've been babbling about here? The relation is very simple. As I said, convex sets are closed under averaging. So once I find this, hopefully as big as possible, convex subset, I simply monitor the geometric condition that my local vector, and every node does it, is inside this purple convex set. As long as it's there, then we're all happy because we know that the average is here and everything is good. But this is, of course, deceptively simple because this admissible region may be a very, very complicated, perhaps even disconnected. It can be a very, very nasty and complicated set in Euclidean space of very high dimension. And the question is what to do. So we have many papers dealing with what to do, and we also have complexity proof. And we actually prove that there is no single, except in some trivial cases, there's no single optimal convex subset. This is a difficult problem, and we've been studying it, as Michael said, for many years, and we're still wrestling with it because it's difficult and interesting. Okay, so this is how it looks. You have this convex subset, which was computed in advance. You have 4 nodes. As long as every node fits inside this nice set, then everything is good. Okay, and the question is how to do it. By the way, I will completely skip the very difficult question of what to do when, for example, node number 2, its vector suddenly moved to here. So what do? Ostensibly, you simply say, okay, I don't know what's happening. I will contact the coordinator. The coordinator will collect all the vectors from all the nodes, compute the average, and see what happens. But there are actually more efficient solutions, and this is something which we are working on now, but I don't have time, of course, to talk about this problem of violation recovery. Okay, so that I will totally forget for now, okay? So this is how it looks, and in the few minutes I have, I will try to say something about how this problem, how we can somehow extract this convex subset, which is suitable for the problem at hand, okay? So this is your problem now, okay? Now, this is, of course, the same expression as before, okay? This very, very familiar expression. However, as I said, now this matrix J is the sum of local matrices, and the vector C, which is multiplied by A minus 1, is also the sum of local vectors. So even if you didn't follow anything until now, just fell asleep, then it's very simple. This is the model. AJ and CJ are local matrices and vectors, and you want to say something about beta, but without centralizing these AJ and CJ. Okay, so how do you do it? Okay, I will have to skip this part, unfortunately, but and I will go directly to here because this is the heart of the algorithm. It's pretty simple, but it was still something which was new. Now you're saying, okay, I have to say something about this inverse times inverse of a matrix times a vector. Now I will try to do the following. I will assume or will denote the change in the matrix A0. 0 is, of course, times 0. And I will denote it by delta, capital delta. And I will denote the change in the vector by small delta. Now I need to find some condition on capital and small data so that this ugly condition holds. Okay? And now it's just linear algebra. okay? And this condition, by the way, has to be convex, because this condition by itself is not convex. Yeah, believe me that it's really absolutely trivial to find numerous examples which violate convexity, so this holds, but the set of delta, capital and small delta, which satisfy this is not convex. But we will at least try to find a nice convex subset which satisfies it. And after all kinds of ugly manipulation, which I will spare you, we find this condition. However, for this condition to hold, we need some auxiliary condition, unfortunately, which is this one, but I will simply swipe this under the rug. This is an annoying technicality, but which has to hold. If it does not hold, then the monitoring fails. However, we have all kinds of probabilistic analysis, etc., which guarantee that this holds, and we can also monitor it directly. I will just say something about this expression. How do you start to handle such an expression? Well, what you do is you take this matrix with A0, which is typically big, and delta, which is typically small, because it's only the change over time relative to what happened in the time zero. And you expand it in a Taylor series, but it's a Taylor series over matrices, so it's kind of ugly, okay? But eventually you get this condition, and this condition, you have to believe me that it's a convex condition. In what? In, of course, delta, capital delta, and small delta. This matrix and this vector, which represent the change over time from the matrix and the vector at time zero. And this is basically it, okay? So you have your, this is just a demonstration of how it works, okay? Node number 1 is good. The data is still here. Node number 2 is good. Node number 3, oops, something bad happened. The local changes, the local delta and delta pair, unfortunately wandered out of the convex phase zone. Then node number 3 will will contact the coordinator, and the coordinator will do something, but this I don't have time to talk about. This is this violation resolution page, which I mentioned before. So I will simply cheat and not talk about it. Then we have this condition, but this I really don't want to talk about because it's even more complicated. So you see, we did something which, as Michael knows, I'm very fond of. Is take a computer science problem and transform it to something which is more mathematical in nature. And then this is something which I like to do because originally I'm a mathematician, so I find this a very nice way to work out things, is to reduce the problem to a mathematical problem. And this can be done, but I will stop here. And I hope I made sense, and that at least generally the problem, the difficulty, and the solution were clear. So I wish to thank you very much, and I will be happy to accept any questions or comments.
Thanks a lot, Danny, for this amazing talk. Now, for all the participants, you now can ask questions. Just raise your hand and I will give you the right to unmute. So maybe while you're still thinking about questions, I definitely have one. First question that came to my mind is, so you already extended it to regularized least squares and generalized least squares, so that's pretty cool. What about going one step further? Could you also solve it in kernel space? So could you solve it for a kernel-rich regression where you basically have to do the same for the dual problem, which is, I guess, much more nasty than...
And that's a good question. And actually, Michael, you are the one who did the first work in this direction. And yes, it's possible, although it gets quite more complicated. Thank you, Katrina, and nice to meet you. And what we did so far, and even that was quite complicated, it's a paper which came out last year, is to do it for just a linear classifier, just the LDA, the good old LDA classifier. And even that was pretty difficult. The general solution in kernel space is not simple, and I have to unfortunately admit that we don't have a closed form solution for it. But this is one of the problems which I mentioned, which is really, really difficult.
I can imagine.
Yeah, definitely. Yeah. Because finding these local conditions can be very difficult, especially if your problem is something which does not have a closed form solution. But good question.
But in principle,
I have a few years till retirement, so I hope to. Okay.
But by the way, you could, I mean, in principle, it would be highly inefficient, but you could do what you did at some point, that is optimize the local conditions for a static problem, right? If you don't do it over streams, you could.
Yes. But once you go, and again, the main problem is that if you look at even a quadratic SVM, okay, then you just don't have a closed form expression. And therefore, it's very, very difficult to do anything. And we ran into some really very, very grave problems for the linear classifier, which we barely managed to solve. And this was a year ago. And now we're looking to extend it. But actually, in recent years, and Michael, you know very well the history of this problem, and you've, of course, made many contributions to it. Currently, we actually found that the more interesting problem, or at least approachable for us, is to do this violation resolution. Because you will always, they keep popping up, these local violations, and most of them are false, okay? So the question is how to resolve them without even one node sending its local data vector to the coordinator. Can we do it? And actually, we devised the method, and we're now working on the paper. We plan to submit it to ICDE, which actually allows, and I'm sorry that I don't have time to elaborate on it, that no matter what the dimension of the data is, we can, in many cases, resolve the violation by sending just one scalar.
Okay, that's interesting.
And that's a kind of, it follows from some non-trivial fact about the geometry of convex. So this is the direction which we found interesting because, as you remember well, in many cases you have a very clever, well, not clever, sophisticated, complicated algorithm, but because you have to keep sending these big data vectors whenever you have a violation, then, you know, especially when the number of nodes increases, then you get, you know, when the number of nodes crosses a certain threshold, then you are hardly beating the trivial algorithm, which keeps centralizing. And this trick, which I mentioned, made a big difference in that respect.
I would be very interested to see that. So
definitely
looking forward to that publication.
And we will, yeah. If it, maybe we will meet again in Crete, but you know,
I would know the perfect place for that.
It will probably be you know, a virtual.
At least for some time. Yeah. Are there any more questions? Do people know how to raise their hand? Right, then maybe one last, just because your answer to the previous one spiked my interest.
Sure.
I saw that the number of false alarms basically also depends on the problem dimension, or the number of parameters in your model vector. Is that correct? At least somehow yes. over this condition A0 times delta smaller or equal to 1 in norm.
Michael, I'm not sure I follow the question. Could you possibly repeat?
The question is, does the number of false alarms depend on the dimension of your model vector? The reason I'm asking is, just let me just give me a bit more context.
Yes,
you could approximate a kernel with a random Fourier feature, but you would usually use a lot more dimensions then.
Good point. In that regard, I have good news. It does not depend that much on the dimension of the data. Usually, the number of these annoying false alarms increases very rapidly with the number of nodes, but not with the dimension of the data.
Oh, but that's pretty good.
And we have some in this paper I mentioned. We have dimension which is in the millions. Okay, and it's actually quite manageable. The big problem is really when the number of nodes increases, because then you have these small local modems, and because they are small, they are noisy, and they can fluctuate a lot. Okay, so if you distribute a huge data set over 10 nodes, then typically each of them will behave nicely and stably. But if you distribute it over 10,000 nodes, then each of them holds a small amount of the data. And although the global behavior is nice, locally, you will very typically have many of these diversions. So this new idea, which I mentioned, is especially helpful in that regard. Of course, we are also very interested and very happy to look at data with a very high dimensionality, because then the reduction in communication is, of course, much larger. If instead of sending the entire vector, you send a scalar. But that's another issue, and it's not the typical cause of false alarm. Yeah.
Awesome. We have one more question. Katharina, I think you're already unmuted.
Yeah, okay.
Hi,
so hi.
Nice to meet
it
you.
was really a very pleasant talk, but could you go back in your transparencies to these slides that came after the variance issue? Because I think this variance issue, that is a real general problem that we have, that the local variance is so different from the global variance.
Right,
and then you calculated these safe and not so safe areas. And there, I must admit, I didn't fully understand how you did it.
Okay, just
So
let
if
me,
you could go back
I guess
there.
I should go back to share screen, right?
Yeah, that would be great.
All good? Okay.
And then further. I didn't write the, it was further.
I will be
further.
happy.
Yeah, that was the situation. That was the
exactly.
situation. And then comes further on, because then comes the, yeah. Further on.
Okay.
I didn't.
Tell me when to stop. Okay.
Yes.
Okay.
So further. I think, yeah, exactly. Here it comes. Then you say you have your previously computed model, and then you have the hypothetical current model.
Yes, exactly. Yes.
Yeah, so where does it come from?
Oh, this beta 0 is simply the model at time 0, which everybody knows.
Yeah.
This is after either when you initialize your entire system or after you resolve a violation.
Okay, yeah.
And so you compute beta 0. Beta is a vector which we do not know. Nobody knows beta. It's a virtual vector. We, of course, have an equation for it, this ugly equation with the matrix inversion. But nobody knows it because we cannot construct this matrix, because then we'll have to communicate all the data.
Exactly. Yeah, that's my question.
Okay, but we do know the equation for it. And therefore, we can still monitor and bound the diversion from this vector. Let me, Katerina, give you some trivial example, okay? Suppose that you were monitoring something really scary, like the determinant of a huge matrix. And you want to know that it did not change by more than 1,000. Then you can very easily find bounds on that and say that, look, if only 2 elements in this matrix changed, and by just something which is bounded by 0.00001, then I do not need to compute the new determinant. I can simply do something ugly and bound the difference and bound the amount by which it changed. So this is something similar, but it's just a bit more complicated. But it does somewhat resemble, because also for this determinant case and also for our problem, you're dealing with the inverse of a matrix. So you're dealing with something which is complicated. So in case I didn't make it clear, then it's very good that you asked. I emphasize, we don't know this beta vector. If we knew it, then everything would be simple. Every every node will simply check that it's beta, that, you simply compute the difference.
Yeah, sure.
But we do not know it. And by the way, Katerina, sorry, just one more sentence. We actually have an earlier paper, which in IPDPS, which deals strictly with monitoring the variance. Okay, so I will be happy if anybody is interested. I will anyway send you the reference.
Oh yeah, that's very good. That's very good, because actually it's not that easy, I thought. You now gave it a simple example, but actually because of the inverse of matrix and because of the communication costs, it is not really very simple in all cases, I thought. Yeah.
No, it's not. And as I said to Michael before, it becomes much more complicated when you look at functions like a kernel, in which you don't even have this closed form expression. It's not even a matrix inverse. It's a very long iterative process, which somehow converges to a minimum, but there's no closed form expression. And this is why it's so difficult, at least for us. I'm sure that somebody smarter than us would be able to.
Thank you.
Thank you very much, Katrina. Take care.
All right, if there are no more questions, let's thank Danny again. That was really a great talk. Also, thanks for the great questions. And with that, so if anybody is interested, I think Danny will at least linger in the chat for a few more minutes. You can just ask him questions directly.